Very good morning to all of you. Can you hear me? मेरी आवाज आ रही क्या आप लोगों को? Very good morning. So we were talking about the kinetics, and in this chapter we have seen. Yes, Rameshwar is saying yes, sir. Okay, chalo. So we were talking about the rates of equations. Sorry, rate of reactions. We have seen the different order of reactions. So, say for example, zero order reaction, first order reaction, second order reactions. Again, in second order reactions, there are two cases are there. Case one is when only one reactant is present. That means in the rate equation, that concentration term have exponent 2. And second case is, that is case 2, if two reactants are there. Okay, that means in rate equation, concentration, there are two concentration term, and each concentration term will have exponent 1, that we have discussed. Again, in case 2, there are two subcases. Subcase 1 is with initial equal concentration, and this subcase 1 is similar to the, very good morning Nutan, Rupesh Kumar, very good morning. Now this subcase 2, again it is similar to the case 1. Please remember this. That means whatever the rate equation we will derive for second order reaction, that is for case 1 and subcase 1, is same. Okay. Now come to the subcase 2. Subcase 2, in that case there are two reactants are present, and these two reactants, their initial concentrations are different or unequal concentration, that we have seen. Okay. Now today we will discuss one more very important point, that is energy of activation. We will discuss today important point, energy of activation, and we will derive a equation, that is differential equation of energy of activation. So we can derive the differential equation for the energy of activation by two ways. So first way is we will apply the Van 't Hoff isochore. First way is by using a Van 't Hoff rule or Van 't Hoff isochore, and second way is by applying Maxwell-Boltzmann distribution law. So these two ways are there, and by using these two way we can derive an equation for energy of activation in its differential form. Okay. So this, what is this energy of activation? What is the importance of energy of activation? Now this energy of activation, you know that we have discussed while discussing the energy profile diagram. Today we will also discuss what is this energy profile diagram and energy of activation. Now this energy of activation, it is nothing but the minimum amount of energy which is required for the reactant molecule to go or to acquire a activated state. That energy is called as a energy of activation. Now how this energy of activation is related to the rate of reaction? Now if energy of activation is high, that means rate constant is low. Energy of activation is high, that means rate constant is low. This energy of activation and a rate constant K, they are inversely proportional to each other. That means higher the energy of activation, lower will be the rate constant, and lower will be the rate of reaction. That means energy of activation is inversely proportional to the rate. Energy of activation is inversely related to the rate of reaction. Okay. Now this energy of activation, you know that it has dimension of energy. It has a dimension of energy, and it plays important role in the rate of reactions. Now how it plays important role, what is the equation for energy of activation, that we will see in today's lecture. Okay. So shall I start today's lecture? Yes or no? Shall I start it now? आ गए क्या सब लोग? So this is your lecture number 5 of chapter number 1, that is chemical kinetics. Chemical kinetics का ये आप लोगों का lecture number 5 चल रहा है. Okay, Rupesh Kumar is saying yes sir, you can start. So we'll start with the Sabha is also there, Prachi is also there. Okay, very good. Sandesh is also there. ठीक है, चलो. So we'll start with the today's topic, that is the effect of temperature on reaction rate. क्या इफेक्ट होता है टेम्परेचर का reaction rate. So we know that increase in temperature, this is a simple point before the energy of activation, because this we have to study, because we will use this effect of temperature, that is vent of isochore, for the derivation of equation for the energy of activation. So what is the effect of temperature on reaction rate? You know that you have discussed while discussing the effect of are factors affecting on the reaction rate, and in that we have discussed five factors we have discussed, sorry, and one factor was effect of temperature. You know that increase in temperature increases the rate of reaction irrespective of its phase, that you have discussed, that you have know very well. क्या होता है, अगर हम लोगों ने टेम्परेचर इंक्रीज किया तो रिएक्शन का रेट क्या हो जाता है, इंक्रीज होता है irrespective of its phase. That means what, whether the reaction takes place in gaseous phase, whether it is takes place in solution phase or liquid phase, it is not important here. So increase in temperature increases the rate of reactions in any phase, whether it is whether it is liquid or whether it is gaseous phase. So how this increase in temperature increases the rate of reaction? So increase in temperature increases the rate constant. इंक्रीज इन टेम्परेचर, अगर हम लोगों ने टेम्परेचर इंक्रीज किया तो रेट कांस्टेंट क्या हो जाता है, इंक्रीज हो जाता है, एंड हायर द रेट कांस्टेंट हायर विल बी द रेट ऑफ रिएक्शन. नाउ हाउ दिस इज, you know that very well. Now according to the want of rule, now let us discuss the what is want of rule. So this is a want of rule. This equation is called as a want of rule, and is this in this equation K is rate constant, T is temperature in Kelvin, here also K is rate constant, and this is want of isochore. Now here n may be positive, the value of n in this equation, it is maybe positive, it is maybe negative, or it is maybe fractional, depending upon the reaction type, depending upon the nature of that reactions. Okay, so this is the want of isochore, and this according to this effect of temperature, the rate of reaction increases. So we'll discuss one general reaction. Okay, this reaction we will take. Consider these reactions. In these reactions there is formation of ether takes place, CH3OCH2O5. this is ether term. So methyl iodide when reacts with C2H5ONa will give you ethyl methyl ether plus NaI, and the data is given, the effect of temperature on the rate constant is given in this table. See here in the column number 2 temperature is given, and this column number 3 rate constant is given, and you know that rate constant is directly related to the rate of reaction. Higher the rate constant, higher will be the rate reaction. Now let us see here at 0 degree Celsius. Here temperature is given in degree Celsius. Temperature is given in degree Celsius. Okay, so at 0 degree Celsius the rate of reaction 0.56 into 10 raised to minus 5. That means it is almost inert. So at 0 degree Celsius the rate of this reaction is very slow. So we can say that at 0 degree there is no reaction. We can say that at 0 degree there is no reaction. Now if we increase the temperature from 0 degree to 12 degree, if we increase the temperature by say 12 unit, so what will happen here, the rate of reaction the rate constant increases to 2.46 into 10 raised to minus 4. And if you compare this two rate constant, so here 4 times there is increase in rate of reaction, here 4 times there is a increase in rate of reaction. ठीक है, क्या हो रहा है, 0 डिग्री से हम लोगों ने 12 डिग्री तक इंक्रीज किया, दैट मीन्स total increase in temperature is 12 degree. So rate constant increases by almost 4 times, and you know that we have discussed, it is observed that while we increase the temperature of any reactions by say 10 degree, there is increase in rate by 2 to 4 times, and in this example it is get very clear. ठीक है, now if you increase the rate of reaction from 12 to 24 degree, again here is increase in rate constant about 4 times. Again here increases the rate of reaction about 4, and from 24 to 20 again it is increases by almost double, 2 times हो जाता है. So increase in it proves that according to this example or data of these reactions, we can say that increase in temperature, say about 10 degree, there is increase in rate constant or rate of the reactions by 2 to 4 times. Okay, so this is nothing but the want of isochore, and now we will start with the Arrhenius equation. So see, this is the Arrhenius equation. This is the Arrhenius equation for energy of activation. D ln K by dt equals to EA by RT square. This K is nothing but the rate constant. D by dt is, it is a small change in concentration at a time t. EA is nothing but the energy of activation. What is this EA? Energy of activation is indicated by EA. This is energy of activation. This is energy of activation. ठीक है. R is gas constant. R is gas constant and T is temperature. T is temperature in Kelvin. See here. I have given. K is rate constant. R is gas constant. T is temperature in Kelvin and EA is energy of activation. And you know that. Sorry. Sorry. Now it is okay. ठीक है. Now we will discuss one more time energy of activation. What is this energy of activation? We will discuss here. See here. For example, this is a energy profile diagram. This is energy profile diagram. Suppose this is your y-axis and this is your x-axis. Okay. And here on y-axis energy is there, and here x-axis reaction progress is there or reaction coordinates is there. And for say for example here reactant is there and here product is there. So what happens, these reactants, okay, and this peak is called as a transition state or activated complex. It is called as a transition state or activated complex. Okay. Now the energy gap between this reactant and this activated state, it is called as the energy of activation. It is called as energy of activation, EA. Now what is this energy of activation? It has dimension energy, you know that, and it is the minimum amount of energy which is required for reactant molecule to go into the transition state or activated complex. This minimum amount of energy, it is called as the energy of activation, and rate is depends upon this energy of activation. Okay, now we'll see the definition. What is the definition? See, if you have pen and notebook, you can write down the definition of energy of activation. Energy of activation is the minimum amount of energy the reactant molecule must acquire before they could react, or must acquire so as they can go to into the transition state or activated complex. So this is a energy of activation, and this is the Arrhenius equation, differential form of Arrhenius equation, and we will derive this equation. And how will you derive? Two methods are there. First we will apply Van-Top isochord, and second way is we will apply Maxwell-Boltzmann distribution law. Okay, so let us start with the derivation of equation by using a Van-Top isochord, and we will consider a very simple reaction, that is A goes to B. Here A is a reactant and B is a product, and for this reaction we will apply a rate law. For this reaction we will apply a rate law. Now rate is equal to minus dCA by dt. So minus sign indicates the concentration of reactants are decreases. Ca is nothing but the concentration of reactant A, which is equal to Kca, which is equal to Kca, and here A is rate constant. What is this K? K is called as a rate constant. Now there are some assumptions. This according to the Van-Top isochord or Van-Top rule, there are some assumptions. So we have to apply those assumptions while deriving the equation. आप लोगों को क्या करना है? Assumptions ठीक से apply करना है while deriving the equation. Now assumption number 1 आपके screen पे है. See, assumption number 1, above reaction could be written in two different steps. This is the first assumptions. A reaction आप लोगों को दिख रही है ना, A goes to B. This reaction, it is not a simple one step reaction according to the assumption number 1. This reaction, it is not a simple one step reaction, so it is a two step reactions. क्या होता है two steps में? So these two steps are there. Let us see first. This reactant A gets the energy EA, that is energy of activation, gets it gets the energy EA and goes into the activated complex. This A is called as activated complex. A star, why star is there? Because it is activated complex. It is a activated complex. So first step is formation of activated complex. It is not a simple single step reaction. It is a two-step reactions. And in first step, what happens? In first step, what happens? In first steps, reactants gets a energy that is called as activation energy and forms a star. Forms a star, that is the activated complex. So from reactant molecule to the activated complex, this is the first step. This is the first step, and again this activated complex, that is A stars, breaks or converts into the product B. So step 2 is nothing but the from the activated complex product formation takes place. This is the first step. So sorry, second step. First step is formation of activated complex and second step is formation of product from an activated complex. So this is assumption number 1. क्या है assumption number 1? Above reaction, it is not a simple one step reaction, it is a two step reaction, and first step is formation of activated complex, second step is formation of product from activated complex. So let us give this equation or reaction number 2. This is our reaction number or equation number 2. ठीक है. Now assumption number 2. Assumption number 2. क्या है assumption number 2? Formation of activated complex is reversible process. So this formation, see these steps I have written in. This arrow indicates a reversible. This arrow indicates it is a reversible reaction. That means if activated complex forms, again that activated complex gets in converts into the reactant molecule. So there may be formation of activated complex, and again from activated complex there again formation of product takes place. Okay, so this is the assumption number 2. क्या है assumption number 2? Formation of activated complex is a reversible process. Very simple assumptions are there. क्या है? Formation of activated complex is reversible process. And if you see here, activated complex to the product, it is not a reversible process. Activated complex to the product, it is not a reversible process. Okay, then assumption number 3. Assumption number 3, listen carefully. Concentration of activated complex is always low. Concentration of activated complex is always low. That means whatever the concentration ये आप लोगों को दिख रहा है ना ये स्टार, इसका concentration क्या होता है? It is always remains low. Why? Because it is a reversible process. Activated complex may convert into the product. That's why उसका concentration हमेशा कैसा रहता है? कम ही रहता है. This is assumption number 3. This is assumption number 3. Now the next step is equilibrium constant for the first step of reaction 2 can be written as. This is your reaction number 2. This is your reaction number 2, and we will apply a equilibrium constant or law of equilibrium. We will apply the law of equilibrium for the first step. That means for these steps only we will apply the equilibrium law for this step. Only for this step we will write down the equilibrium constant, and this equilibrium constant is denoted by Kc. Equilibrium constant is denoted by Kc. And what is the definition of equilibrium constant? It is the ratio of product of concentration of product to the product of concentration of the reactant. It is a ratio. किसका ratio? Product of concentration of product. So here in this case the product is A star. It is a product. It is a product, and these are Ca is a reactant. So it is the ratio of product of concentration of product. So concentration of A star divided by concentration of A. It is a product and it is a reactant. So it is a ratio of concentration of product to the product of concentration of reactant. Or we can write, we will rearrange this Ca. If we take this Ca into this side, then C star A will become Kc into Ca. This is our equation number 3. This is our equation number 3. Then now we will apply on top isochore to the equilibrium constant. ये जो दिख रहा है ना, for this we will apply a one top isochore to the equilibrium constant from the equation number 3. Equation number 3 का जो equilibrium constant है Kc, to this Kc we will apply a one top isochore, and after applying one top isochore you will get dln Kc. We will get here, see here, dln Kc by dt is equal to EA by RT square. After applying one top isochore, we will get this equation. D ln Kc by dt equals to EA by RT square. This is our equation number 4. This is our equation number 4. Okay. Now assumption number 4. Now last assumptions क्या है? Activated complex once formed is converted into the product at a rate which is does not depends upon the temperature. Now here activated complex form Y. This activated complex get converts into the product at a rate, और इसका rate जो होता है it is does not depends upon the temperature. It does not depends on temperature. So the temperature dependent कौन सी step है? Only first step is temperature dependent step. Second step it is not a temperature dependent step. That is formation of product from activated complex is not a temperature dependent step according to the assumption number 4. The only one step which is temperature dependent, that is step number 1. That is formation of activated complex is a temperature dependent step, and formation of product from activated complex is not a temperature dependent step. Please remember this. This is your assumption number 4. Okay. Now by considering all the assumptions, rate of formation of product can be written as, now we will consider all the assumptions and we will write down the rate of formation of product. So we will write here according to the all assumptions, rate is equal to dCb by dt, which is equal to constant C star A, which is equal to constant Kc into Ca. So this is the result of all 4 assumptions. This is the result of all four assumptions. Now we will compare equation number 1 and 2. We will compare equation number 1 and 2. We will get K is equal to constant Kc. We will get K is equal to constant Kc, and if we solve this equation, ln K is equal to ln constant plus ln Kc. This is our equation number 5. This is our equation number 5. Okay. Now we will differentiate. We will differentiate this equation number 5 with respect to temperature, and after differentiating we will get, so we will differentiate. So after differentiating we will get d ln K by dt. Here d ln K after differentiating with respect to temperature, this d by dt, and here please remember d is written as a in capital letter, so it is a temperature in Kelvin. Please remember this. So d ln K by dt is equal to d ln K C by dt. So after differentiating equation number 5, we will get this equation. We will get this equation, and from equation number 4 we can write, or we can get, now we have to compare this equation. We have to compare this equation with equation number 4. We will get d ln K by dt equals to EA by dt square, and this is our Arrhenius equation in differential form. This is our Arrhenius equation जो हम लोगों ने starting में देखा था ना. This is our Arrhenius equation in differential form, and this is according to the one top isochore. This is according to the one top isochore. So this is the first way to derive Arrhenius equation. d ln K by dt equals to EA by dt square. This is your Arrhenius differential form of equation according to the one top isochore. Now we will consider or we will derive the equation of energy of activation by using Maxwell-Boltzmann distribution law. This is the second way we can derive the equation, by using a Maxwell-Boltzmann distribution law. Now see here, this equation is called as a Maxwell-Boltzmann distribution law. NEA by NT equals to E exponential or E raised to minus EA by RT. This is our equation number 6. Now in this equation, if you see, only NEA molecules are capable, these molecules are capable of reacting, hence we can write rate of reaction. क्या होता है? According to this equation, only NEA molecules, those molecules, NEA molecule means those number of molecules which can take energy of activation, that molecule is capable of reacting. Okay, what is the meaning of this NEA? Those molecules we can get the minimum amount of energy, that is energy of activation EA, only those molecules are capable of reacting. Hence according to this we can write rate of equation. According to this we can write rate of equation is equal to E A NEA. That means only these molecules, they are capable, whatever the value of N is, 2 molecules, 4 molecules, जो कुछ भी वैल्यू है, that molecules are capable of reacting ये. So रेट किसके ऊपर डिपेंड होगा? Only those molecule which can acquire energy of activation, उसके ऊपर ही रेट डिपेंड होगा ना. And what is this A here? What is this A? It is called as a proportionality constant or Arrhenius constant. This A is nothing but the proportionality constant or Arrhenius constant. Now we will substitute this NEA from equation 6 and 7. We will get rate of reaction equals to A NTE raised to minus EA by RT. So this we will get after substituting this value. ठीक है. Now हम लोगों को ये मिल गया रेट ऑफ इक्वेशन A NT E exponential EA by RT. No dot is here. EA by RT. So this is our equation number 8. And here NT is the number of molecules per unit volume equals to concentration of reactant C. So equation number 8 becomes, equation number क्या हो जाएगा? Rate of equation number 8 will become now rate of equation equals to A into C, because NT is equals to C. NT is equals to C. A into C into E raised to EA by RT. This is our equation number 9. And also in this equation rate of reaction is replaced by C by the relation rate of reaction is equal to K into C. Rate of reaction is equals to K into C. This is your reaction, this is your relation. Now rate of reaction is replaced by C, so we will replace rate of reaction by C. We will get by comparing equation 10 and 9. By comparing the equation 9 and 10, we will get this equation. K is equal to the rate of reaction is nothing but the K is equal to K is equal to A into E raised to EA by RT, and this is your Arrhenius equation in differential form according to the Maxwell-Boltzmann distribution law. This is your Arrhenius equation. K is equal to A into E raised to EA by RT. This is the Arrhenius equation in differential form, Arrhenius equation according to the Maxwell-Boltzmann distribution law. ठीक है. ठीक है. Now you will realize that in this equation lot of mathematical term is involved, lot of mathematical operations are involved in this equation. ठीक है. So due to this mathematical part will stop here, because those are having mathematics background, they can उन लोगों के लिए तो ये इजी है, but those do not have mathematical background, for them it is a little bit difficult. So we will take very short portion in each lecture so that you can understand it clearly. So we will stop here. Today we will stop here. If you have any problem, any doubt about today's lecture, you can ask me. I will give 5 minutes for that, and after these 5 minutes, I will active the link for your attendance. You can give the attendance. ठीक है. Now if you have any problem, any doubt, you can ask me. क्योंकि बहुत से सारे मैथमेटिकल एक्सप्रेशंस है इसमें, तो जिन लोगों को मैथमेटिक्स है उनके लिए तो ये इजी है, जिन लोगों को मैथमेटिक्स नहीं है उनके लिए ये थोड़ा सा डिफिकल्ट हो सकता है. Now if you have any problem, any doubt, you can ask me. No doubt. Very good. That means you have understood. All are having mathematical background. किसको किसको मैथ था और किसको किसको मैथ है? नो सर, थैंक यू. अच्छा, नूतन को तो कोई डाउट नहीं है. नूतन का मैथ्स होगा शायद. ओके, नो प्रॉब्लम, कोई डाउट नहीं है, अच्छी बात है. Abhishek is saying no sir, I have maths. अच्छा ठीक है, अभिषेक को मैथ है. सो मैथ्स पीपल, तो उनके लिए तो कुछ नहीं है इसमें, लेकिन जिसको जिसको मैथ नहीं है ना, उसको उसको थोड़ा थोड़ा प्रॉब्लम आ सकता है. तो उन लोगों को क्या करना चाहिए, प्रैक्टिस करनी चाहिए. They have to practice it. Solve 2 to 3 times each equations, each derivations. Istishami Singh sir, what about collision frequency in solution state? Oh, अभी वहां तक आना है मुझे. Let me finish it step by step. Istisham, we will discuss it. Don't worry about that. We have to discuss collision theory also. Probability factor is also there. Don't worry about that. We will discuss it. ठीक है. Istisham, please ask me about today's lecture. Now I have activated the link for your attendance. Huh? I have activated the links for your attendance. You can give the attendance also. Yes, any problem? No problem. So, shall I stop here now? Maybe. Shall I stop now? Okay. So, with this, Rupesh Kumar is saying no any problem, sir. So, no more problem, no more questions. So, I will stop here. Bye bye. Take care. Have a good day.